Welcome to Selection with Sathi. Today we master bit manipulation, a topic that appears in GATE CSE, placements, and competitive coding. We will cover binary representation and/or XOR operations, bit shifts, common tricks like check set and clear bit, 2's complement, and 5 powerful examples. Let us begin. Let us start with binary representation. Look at the code on the left. The number 13 in binary is 1101. That means 1 times 8 plus 1 times 4 plus 0 times 2 plus 1 times 1 equals 13. Each position I from the right represents 2 to the power I. In Python, bin of 13 gives the string 0b1101. To convert back, int of the binary string with base 2 gives 13. To check a specific bit at position I, shift n right by I positions and with 1. If the result is 1, that bit is set. An n-bit unsigned number can represent values from 0 to 2 to the n-1. Now the 3 fundamental bitwise operations. Look at lines 3 through 5. We have a equals 12, binary 1100, and b equals 10, binary 1010. And 1100 and 1010 gives 1000, which is 8. A bit is 1 in the result only if both input bits are 1. Or 1100 or 1010 gives 1110, which is 14. A bit is 1 if either input is 1. XOR 1100 XOR 1010 gives 0110, which is 6. A bit is 1 only when the inputs differ. XOR has 3 key properties: A XOR A equals 0, A XOR 0 equals A, and it is both commutative and associative. Bit shifts are incredibly powerful. Look at line 3, x equals 5, binary 101. Left shift by 1101 becomes 1010, which is 10. That is 5 times 2. Left shift by 3101 becomes 101000, which is 40. That is 5 times 8. Right shift by 1101 becomes 10, which is 2. That is 5 divided by 2, integer division. The most important use, 1 left shift I creates a mask with only bit I set. For example, 1 left shift 3 gives 1000, which is 8. This mask is the building block for checking, setting, and clearing individual bits. Shifts array O of 1 operations, much faster than multiplication or division. 4 essential bit manipulation operations. Look at line 2, check bit. Shift n right by I and with 1. This isolates just bit I, giving you 0 or 1. Line 5, set bit. Or n with 1 left shift I. This forces bit I to 1 without changing any other bits. Line 8, clear bit. And n with the complement of 1 left shift I. The complement flips the mask, so all bits are 1 except bit I, which becomes 0. Line 11, toggle bit. XOR n with 1 left shift I. If bit I is 0, it becomes 1. If it is 1, it becomes 0. These 4 operations are the foundation of all bit manipulation problems. 2's complement is how computers represent negative numbers. Look at the code. Plus 5 in 8 bits is 0000, 0101. To get -5, first flip all bits to get 1111, 1010. Then add 1 to get 1111, 1011. That is -5 in 2's complement. The formula is -x equals complement of x plus 1. The most significant bit is the sign bit. 0 means positive, 1 means negative. For 8 bits, the range is -128 to +127. For 32 bits, it is -2 to the 31 to +2 to the 31 minus 1. A useful trick, x and -x gives the lowest set bit of x. This is used in binary indexed trees and many bit manipulation problems.
Let us check if a number is a power of 2. Look at line 2. The trick is n and n minus 1 equals 0. Why does this work? A power of 2 has exactly one set bit. 16 is 10000. 15 is 01111 and gives 00000. So 16 is a power of 2. 8 is 01000. 7 is 00111 and gives 00000. Power of 2. Now 18 is 10010. 17 is 10001 and gives 10000, which is not 0. Not a power of 2 because 18 has 2 set bits. The key insight, n and n minus 1 always clears the lowest set bit. If the result is 0, there was only one set bit, meaning power of 2. This runs in O of 1 time. No loops needed. Brian Kernighan's algorithm to count set bits. Look at line 4. In each iteration, n and n minus 1 clears the lowest set bit. We count how many times we do this until n becomes 0. Let us trace n equals 29, binary 11101. Iteration 129 and 28 equals 11100, which is 28. Count is 1. Iteration to 28 and 27 equals 11000, which is 24. Count is 2. Iteration 324 and 23 equals 10000, which is 16. Count is 3. Iteration 416 and 15 equals 00000, which is 0. Count is 4. The answer is 4 set bits. The beauty, this runs in O of k iterations where k is the number of set bits, not all 32 bits. Much faster than checking each bit individually. Find the unique element using XOR. Array 4, 1, 2, 1, 2. Every element appears twice except 1. Look at line 4. We XOR all elements together. Start with result equals 0. XOR with 4 gives 4. XOR with 1 gives 5. XOR with 2 gives 7. XOR with 1 gives 6. The two ones cancel each other. XOR with 2 gives 4. The two 2's also cancel. Only the unique element 4 survives. This works because A XOR A equals 0 and A XOR 0 equals A. All pairs cancel to 0, leaving just the unique element. O of n time, O of 1 space. No hash maps or sorting needed. Swapping to numbers without a temporary variable using XOR. Start with A equals 5, binary 0101, and B equals 9, binary 1001. Line 2, A becomes A XOR B, which is 0101 XOR 1001 equals 1100, which is 12. Line 3, B becomes A XOR B, which is 1100 XOR 1001 equals 0101, which is 5. Now B holds the original value of A. Line 4, A becomes A XOR B, which is 1100 XOR 0101 equals 1001, which is 9. Now A holds the original value of B. Swap complete. The trick relies on A XOR B giving back A. In practice, use a temporary variable for clarity, but this is a classic interview question. Generating all subsets of a set using bit masks. For array A, B, C with 3 elements, we iterate mask from 0 to 2 to the 3 minus 1, that is 0 to 7. Look at line 6. For each mask, we check which bits are set. If bit I is set, include element I in the subset. Mask 0 is 0, 0, 0, empty set. Mask 1 is 0, 0, 1, just A. Mask 2 is 0, 1, 0, just B. Mask 3 is 0, 1, 1, A and B. Mask 4 is 1, 0, 0, just C. Mask 5 is 1, 0, 1, A and C. Mask 6 is 1, 1, 0, B and C. Mask 7 is 1, 1, 1, A, B, and C. Total 8 subsets, which is 2 to the 3. This technique is used in competitive programming for problems involving subsets, combinations, and bitmask DP.
Quick exam tips. First, n and n-1 clears the lowest set bit. Use this for power off to check and Brian Kernighan's set bit counting. Second, XOR has 3 key properties. A XOR I is 0, A XOR 0 is A, and it is commutative and associative. These solve many array problems in O of 1 space. Third, left shift by k multiplies by 2 to the k, right shift by k divides by 2 to the k faster than arithmetic operators. Fourth, in gate bitwise operation questions, trace each bit position independently. Do not convert to decimal midway. For more DSA concept videos with code walkthroughs, download the Selection with Sathi app. Like and subscribe. Thank you.